The bond length and bond strength in molecules have an inverse relationship. The shorter the bond, the stronger it is, and vice versa. So for example, a carbon-carbon single bond is longer but weaker compared to a double bond or a triple bond. And so a triple bond, a carbon-carbon triple bond, is stronger than a double bond, and a double bond is stronger than a single bond. Likewise, a carbon-carbon triple bond is shorter than a double bond, and a double bond is shorter than a single bond. So in that case, single bond is the longest and the weakest among the three types of bonds here. It also means that it's harder to break a triple bond compared to a double bond or a single bond. So that means that it's easier to break a single bond than a triple bond. And since the hybridization of a bond is linked to the type of bond, single bond versus double versus triple bond, the bond length and strength are also related to the hybridization of the bonds. So for example, an sp3 hybridized carbon is basically a single bond, an sp2 hybridized carbon is a double bond, and an sp hybridized carbon is a triple bond. And so an sp hybridized bond is stronger but shorter than an sp3 hybridized bond. And again, this is a triple bond, this is a double bond, and this is a single bond. So the triple bond is shorter but stronger compared to a double bond or a single bond. Here's a table summarizing the relationship between bond length and bond strength of the different types of bonds in organic compounds. So here we have three different compounds. We have ethane, ethylene, and acetylene. So these are organic compounds containing two carbon atoms. So we have a single bonded carbon atoms, double bond, and triple bond. So the single bonds are sp3 hybridized, the double bonds are sp2 hybridized, and the triple bonds are sp hybridized. So when you look at the carbon-carbon bond length, you can see that the triple bonds are the shortest at 121 picometers, and the single bonds are the longest at 153 picometers. So you can see that the sp hybridized bonds are the shortest compared to sp2 or sp3 hybridized bonds. But when you look at the bond strength, you can see that the triple bonds or the sp hybridized triple bond is the strongest at 837 kilojoules per mole compared to the double bond or the single bond. So this trend can also be observed in carbon to hydrogen bonds. So here we have an sp3 hybridized carbon to hydrogen bond. The second one is sp2 hybridized, and then in acetylene, it's sp hybridized. So comparing the bond length and strength, you can see that the trend in carbon to hydrogen bond length increases from sp hybridized bonds to sp3 hybridized bonds, which is similar to the trend observed for carbon to carbon bonds. But it's also reversed when it comes to bond strength. So you can see that the sp hybridized carbon hydrogen bond is the strongest compared to the sp2 and the sp3 hybridized carbon hydrogen bond. The trends in the bond length and strength can be attributed to the percent S character of a bond. This concept indicates the fraction of a hybrid orbital due to the 2s orbital used to form it. A 2s orbital keeps the electron density closer to a nucleus in comparison to a 2p orbital. Therefore, as the percent S character increases, a hybrid orbital holds its electrons closer to the nucleus, and the bond becomes shorter and stronger. An sp hybrid orbital contains one s orbital and a p orbital for a total of two hybrid orbitals. So 1 divided by 2 gives us half, which is basically 50% s character. An sp2 hybrid orbital contains one s orbital and two p orbitals for a total of 3. So 1 divided by 3 gives us 33% s character. And the last one here, sp3 hybrid orbitals contain one s orbital and 3 p orbitals for a total of 4. So 1 divided by 4 gives us 25% s character. So again, an sp hybrid orbital or a hybridized bond is basically a triple bond, and an sp2 hybridized bond is a double bond, and an sp3 hybridized bond is a single bond. And so a triple bond contains more s character than a double bond or a single bond. So the higher the percent S character, the shorter and the stronger the bond. The smaller the percent S character, the longer and the weaker the bond. Here's practice problem number 33. Which of the bonds shown in red in each compound or pair of compounds is shorter? So for the first one here, we have an sp hybridized triple bond versus an sp2 hybridized double bond. So when you're comparing the two, we know that a triple bond is generally shorter than a double bond. So this one is shorter. All right. And what about the second one here? So for this bond right here, this one is sp3 hybridized. And this double bond right here is sp2 hybridized. So the fact that this is a double bond makes it a shorter bond. All right, let's take a look at this third one here. So we have this carbon that's single bonded to a hydrogen, and we have another carbon that's also single bonded to hydrogen. So in order to compare the length of these bonds, we have to look at the hybridization of the bond. And so when we look at this carbon right here, it contains 1, 2, 3 electron groups. So that means that this is sp2 hybridized bond. Whereas this one, the carbon, contains 1, 2, 3, 4 bonds or 4 electron groups. So that means that this is sp3 hybridized. So an sp3 hybridized bond, carbon to hydrogen bond, is longer compared to an sp2 hybridized carbon hydrogen bond. So this one is shorter. And the last one here, we have a nitrogen-hydrogen bond. So again, we're comparing the hybridization of these two bonds. So the first nitrogen here has 1, 2, 3 electron groups, which makes this bond sp2 hybridized. Whereas this bond here on the second molecule, this nitrogen has 1, 2, 3, 4 electron groups, which makes it sp3 hybridized. And so again, this bond here, the sp2 hybridized bond, is shorter. Here's practice problem number 34. Rank the labeled bonds in xanthalpic acid, a fatty acid obtained from the seeds of the sandalwood tree used in cosmetics, in order of increasing bond length. So the first thing that I would want to do here is to redraw this part of the molecule using Lewis structure, so you can clearly see the carbon atom. So it looks something like this. And so we're going to have to analyze the hybridization of the carbon atoms that are involved in the bonding. So that means that we're going to look at these bonds here. So there's 1, 2, 3, 4, which basically corresponds to these 4 highlighted bonds here. And now we're going to have to analyze every single one of these carbons and see what the hybridization is for every single one of them. And so, for example, this carbon contains 1, 2, 3, 4 electron groups, so it's sp3 hybridized. So this is sp3 hybridized carbon. This carbon, on the other hand, only has 1, 2, 3 groups, and so this is sp2 hybridized. This carbon here is sp2 hybridized. However, this carbon only has 2 electron groups, so this is sp hybridized. And then this carbon is also sp hybridized. This carbon should contain 2 more bonds, so I'm going to include that over here. So this carbon is sp3 hybridized as well. And then both of these atoms, or carbon atoms, are sp3 hybridized. So this bond right here was labeled 1. So this is 1, the first bond. This is the second bond. This is the third bond. And this is the fourth bond. So now looking at these 4 different bonds, 1, 2, 3, and 4, the first bond is between an sp3 carbon and an sp2 carbon. So we're just gonna write it down here. We have a carbon that's sp3 bonded to a carbon that's sp2. And then for the second one, we have a carbon that's sp2 hybridized bonded to an sp hybridized carbon. All right, and here's all of them. And so you learned in the previous slide that an sp3 hybridized bond is the longest compared to an sp hybridized bond. So let's write that down. So sp3 is the longest, followed by sp2, and then sp. So sp3 is the longest, and sp is the shortest. So now we're going to analyze these different bonds here. So you can see that bond number 4 is a carbon-to-carbon sp3 hybridized bonds. So you can see that this would be the longest because of the fact that both carbon atoms are sp3 hybridized. So we're going to write it down here. This is the longest. Followed by, I would say this one right here, because this is sp3 to an sp2 hybridized carbon. So this one is the second longest. And then between the two here, this is sp2 versus an sp, and we know that sp3 is longest compared to sp2 and sp. So number 3 would be the third longest, and then the second bond would be the shortest. So now this problem asks to arrange the bonds in order of increasing bond length. And so in that case, 4 is greater than, let's see, 1, and 1 is greater than 3, and then 3 is greater than 2. And so this is arranged in decreasing bond length, and so you can just reverse this. So that would be 2 is less than 3, and 3 is less than 1, and 1 is less than 4. So that would be the answer, right, in terms of increasing bond length. 4 is the longest, and 2 is the shortest. Another trend in the periodic table is electronegativity. And electronegativity is defined as the measure of an atom's attraction for electrons in a bond. And electronegativity increases from left to right towards fluorine, and from bottom to top also towards fluorine, because fluorine is the most electronegative element in the periodic table. Here's practice problem number 35. Rank the following atoms in order of increasing electronegativity. Label the most electronegative atom and most electropositive atom in each group. So for the first one here, looking at the periodic table, the arrangement looks something like this. So we have an oxygen atom, sulfur, and selenium. And so we know that electronegativity increases as you move up towards fluorine. So increases in this direction. So in that case, oxygen would be the most electronegative, and selenium is the least electronegative, or the most electropositive in this group. The next one here, we have phosphorus, sodium, and chlorine. So in the periodic table, this is basically arranged in this order. So we have sodium, phosphorus, and then chlorine. And so electronegativity increases in this direction towards fluorine, and chlorine is right next to fluorine. And so it increases from left to right. And so in that case, chlorine is the most electronegative here, and sodium is the most electropositive because it's the least electronegative. And the third one here, we have chlorine, sulfur, and fluorine. In the periodic table, we have this specific arrangement. So we have the sulfur, followed by the chlorine, and then right above it is fluorine. And so the electronegativity increases from left to right, and then from bottom to top towards fluorine. And so fluorine is the most electronegative in this case, and sulfur is the most electropositive. So again, it increases from top to bottom and from left to right. And finally, for part D, we have oxygen, phosphorus, and nitrogen. In the periodic table, this is arranged in this order. We have phosphorus, and right above it is nitrogen, and then oxygen right next to it. And so again, electronegativity increases from bottom to top, and then from left to right. And so in this case, oxygen is the most electronegative in this group, and phosphorus is the most electropositive. Electronegativity values are used to indicate whether the electrons in the bond are equally shared or unequally shared between two atoms. When the electrons are equally shared, then the bond is considered nonpolar. However, if the electrons are unequally shared, then the bond is considered polar. This carbon-to-carbon bond, for example, is considered a nonpolar bond because the electronegativity difference between them is practically zero. This bond between carbon and hydrogen is actually also considered nonpolar because of the fact that the electronegativity difference between carbon and hydrogen is minute. Bonding between atoms of different electronegativity values results in unequal sharing of electrons. For example, in the carbon to oxygen bond, the electrons are pulled away from the carbon towards oxygen because the oxygen is the more electronegative element. The bond is considered polar or polar covalent. The bond is said to have a dipole because of the fact that there's a separation of charge. So for example, the carbon receives a partial positive charge, and the more electronegative atom receives the partial negative charge. So this difference in electronegativity creates a dipole, or a separation of charge. So in other words, this bond between the carbon and oxygen is considered polar, or polar covalent bond. The direction of the polarity points towards the more electronegative atom, and so you have this polar vector, which basically points towards oxygen, the more electronegative atom. Here's practice problem number 36. Show the direction of the dipole in each bond. Label the atoms with partial positive and partial negative. So looking at hydrogen fluoride, for example, fluorine is the more electronegative atom. So this atom will receive the partial negative charge. So this is partial negative, and then the hydrogen will receive a partial positive charge, and so the direction of the dipole will be towards the more electronegative element. For the second one here, we have boron and carbon. Between boron and carbon, carbon is the more electronegative atom. So in that case, carbon will receive the partial negative charge, and the boron the partial positive charge. And the direction would be towards the more electronegative element, which is in this case carbon. Between carbon and lithium, carbon is the more electronegative element, and so it will receive a partial negative, and lithium will receive the partial positive, and so the direction of the dipole will be towards carbon. For part D, we have carbon versus chlorine, and chlorine here is the more electronegative element, and so it will receive a partial negative, whereas the carbon will receive a partial positive charge. And so the direction of the dipole will be towards chlorine, the more electronegative element. So knowing the polarity of molecules is extremely important because it allows you to determine and predict whether a molecule is going to be soluble or insoluble in a specific solvent. So you've heard of the term or phrase like dissolves like. So what that means is that polar molecules are soluble in polar solvents. Likewise, nonpolar molecules are soluble in nonpolar solvents, but polar molecules are insoluble in nonpolar solvents. And in addition, nonpolar molecules are also insoluble in polar solvents. And so that's basically the importance of learning the polarity of molecules. So how do we determine the polarity of molecules? So there are two things that you're going to need. The first one is the polarity of the bonds, the individual bonds within that molecule. And the second thing is the geometry of the molecule. Is the molecule linear, trigonoplanar, tetrahedral, so on and so forth. And then you're going to combine those two things to determine whether you have what they call a net dipole for that entire molecule. And so in order to determine whether the bonds are polar or nonpolar, you have to look at the electronegativity of the two atoms. So for example, if you have a carbon to chlorine bond, then that bond between them is considered polar because there's a large electronegativity difference between carbon and chlorine. But if you have a carbon to hydrogen bond, then that's considered nonpolar. If you have a carbon to carbon bond, that's also considered nonpolar because there's zero difference in their electronegativities. So polarity of the bonds is very important, as well as the geometry of the molecule itself. So once you've taken into account the polarity of the bonds, the individual bonds within that molecule, as well as the geometry of the molecule itself, then you'll be able to determine the polarity of the molecule by looking at the overall dipole of that molecule. If the overall dipole of the molecule is zero, then that molecule is considered nonpolar. However, if the overall dipole of that molecule is non-zero, then that molecule is considered polar. So here's an example. So we have the Lewis structure for water, and you can see that water has a bent geometry. And analyzing the two bonds in water, you can see that each single bond is considered polar because of the fact that there's an electronegativity difference between oxygen and hydrogen. And so there's a separation of charge. So the partial positive will be on the hydrogen and the oxygen will receive a partial negative charge. And so the dipole points towards the more electronegative element, which in this case is oxygen. And so both dipole vectors here point towards oxygen. And so when you add the two vectors, the two dipoles, then you have an overall dipole that's pointing up. All right, and so this molecule has a net dipole, which means that this molecule is polar. So water is a polar molecule. Here's another example. So this is the Lewis structure for carbon dioxide, and you can see that carbon dioxide is a linear molecule. And the bonds between carbon and oxygen here is considered polar. So this carbon to oxygen bond here is polar, and this carbon to oxygen bond here is also polar because of the fact that there's an electronegativity difference between carbon and oxygen, where oxygen is the more electronegative atom. And so because of that, the oxygen will receive the partial negative charge, and the carbon, the less electronegative atom, receives the partial positive charge. And so what we have here is a separation of charge. In other words, a dipole. So the bonds are considered polar, but the molecule itself is actually considered nonpolar. And here's why. So when you draw the vectors, the direction of the dipole, they point towards the more electronegative element, which is oxygen. And so because the direction for the dipoles are opposite, they cancel each other out. So what you get is a net dipole of zero. The overall dipole for this molecule is zero, which suggests that carbon dioxide is a nonpolar molecule. Here's practice problem number 37. Indicate which of the following molecules is polar because it possesses a net dipole. Show the direction of the net dipole if one exists. So let's take a look at CH3Br here. So the first thing that you want to do here is to draw the Lewis structure for this molecule so that you can determine its geometry. Okay, so we know that we have 3 hydrogen atoms bonded to the carbon atom and bromine that's also bonded to the carbon atom. So in that case, the central atom, carbon, has 4 electron groups as shown here. So this is the molecular structure, the Lewis structure for this molecule. And as you can see, the central atom, carbon, has 4 electron groups, 1, 2, 3, and 4, which makes this molecule tetrahedral. And so now you can determine the polarity of the bonds. So we know that the carbon to hydrogen bonds here are nonpolar because of the fact that the electronegativity for carbon and hydrogen is basically the same. And so the only thing that we're really looking at is the polarity of this bond here between carbon and bromine. And so you can see that the electronegativity of bromine is larger compared to carbon. And so bromine in this case will receive a partial negative charge. Whereas carbon, the electropositive atom here, will receive a partial positive charge. And so we have a net, so this bond is basically polar. And the direction of the dipole points towards bromine, the more electronegative atom. All right, and so because the difference between carbon and hydrogen in terms of electronegativity is practically zero, the overall dipole of this molecule is non-zero. And because it's non-zero, this molecule is going to be considered polar. Alright, so what about the second one here? We have CH2Br2. Again, the carbon atom is going to be the central atom, and we have 2 hydrogens bonded to it, as well as 2 bromine atoms bonded to the carbon atom. And so when you draw the Lewis structure, it looks something like this. So as you can see, the carbon atom again has 4 electron groups, which suggests that this molecule is tetrahedral. And we know that again the carbon to hydrogen bond is basically nonpolar, and the carbon to bromine bonds are considered polar. And so the bromine will receive a partial negative charge and carbon partial positive charge. And so the direction of the dipole will be pointing towards the bromine atom. And again, the overall dipole of this molecule is going to be non-zero. And this suggests that this molecule is going to be a polar molecule. And the overall net dipole will be pointing towards basically in this direction. Because when you add the 2 polar vectors, it'll be pointing in this direction. And for this third one here, we have CF4, and so again we have 4 atoms that are bonded to the carbon atom, the central atom. So automatically that carbon is going to be tetrahedral, meaning it has 4 bonds connected to it. So when we draw the Lewis structure, it looks something like this. So we have a carbon atom with 4 fluorine atoms bonded to it. And so when you look at the polarity of the bonds, you can see that all these bonds are considered polar because there's a net difference in their electronegativity. So we know that fluorine is a more electronegative atom compared to carbon, and so fluorine will receive the partial negative charge. And carbon will receive the partial positive charge. And so then the direction of the dipole will point towards fluorine. And because the dipole vectors are pointing in opposite direction, they basically cancel each other out. And so the net dipole here, or the overall dipole, is going to be 0 for this molecule. So in that case, CF4 is considered nonpolar. And for this fourth one here, we have the Lewis structure that's already drawn for you. So we know that the chlorine atoms are more electronegative than the carbon atoms, and so they will receive the partial negative charge. And the electropositive carbons will receive a partial positive charge. And so in that case, the direction of the dipole will be pointing towards the more electronegative atom. And because these two dipoles are not exactly opposite each other, there's going to be a net dipole. So this molecule is going to be a polar molecule. And the last molecule here is basically similar to the fourth molecule, except the location of the chlorine is at the bottom. So again, the chlorine atom is the more electronegative atom, and so the dipole will be pointing towards chlorine. And now you can see that the direction of the dipoles are opposite, and so they cancel each other out. Therefore, this molecule is nonpolar.